Hey there, it's Joseph from RoboFlow. Today's discussion, we're going to focus on evaluating different model architectures. Why is it you choose one model over another? What sort of trade-offs do you have to consider? You want to open this up with what is it that you should be thinking about when comparing one machine learning model versus another?
Yeah, so I think there are just kind of a few broad categories, and then we'll kind of dive in and start to take apart each one of these categories in isolation. But the uh, main things you need to be considering are how fast is your model going to train? How fast is it going to inference? How well is your model going to perform? And then also, after you've kind of weighed all of those in place, you need to start thinking about deployment. So what's the model size of your model, like in terms of just raw storage, and then also where can you deploy your model. So in computer vision, that becomes really relevant, where you're thinking, do you need real-time object detection or real-time detection, or do you is some latency okay? Can you do it on the server side, and where can you actually put your model once you're done? So those, I think, are kind of the main components that you're weighing as you're thinking about different model architectures.
Yeah, yeah, I think that makes a ton of sense. And the components there that are interrelated is really like model performance in terms of its speed and its accuracy and model size and how that determines, as you were mentioning, deployment environment and otherwise, right? So if you have a large model, you would, in terms of number of parameters and therefore in terms of size of that model, in terms of the number of megabytes that it takes up, you would generally expect that model to be more accurate, right? Because it has greater granularity, it can be fine-tuned to be a bit more performant, but also likely slower performing, right? Inference just takes a bit longer and it takes more computational power. And in that side of things, you're probably going to be considering server-side deployment. I don't know like large models that you're going to be able to get away with deploying on device, um, but maybe I'm wrong. Like if we're thinking about that as one of the trade-offs, like where is the line? Like which architectures might fall into one corner versus another? Is this going to change over time? Like how do you think about that?
Yeah, certainly. And I mean, it's definitely an exciting time to be in computer vision from that standpoint, in that the compute capabilities of uh, different compute engines like GPUs and Movidius VPUs, and there are TPUs, and there's all the different U's now that you can be deploying things to. It's just vastly increasing. So the size of these models that we're able to actually deploy to the edge is ever increasing, and not only on the hardware side, but also on the software side. There are frameworks like OpenVINO and uh, NVIDIA's TensorRT, which are speeding up the speed of computations on these things. So you're actually starting to get even more performant models that are larger, that you can deploy at faster speeds. So that's definitely kind of changing the game and reawakening architectures that previously were kind of monolithic and were unable to be wielded. But certainly the dichotomies here that Joseph has been elaborating on the fact that a larger model is going to perform better, and it's going to infer slower, is just kind of always going to be a brute fact. And state of the art for a lot of these tasks will always be with these extremely large models that are trained on, you know, many TPUs.
Yeah, efficient debt comes to mind there, right? That's why efficient debt, they released D0 to D7, um, and yeah, the of course if you have the resources of a Google, it's just fundamentally different than elsewhere. I'm going to ask sort of a question. So, like, if you think about this and you extend out 10, 20, 30 years, what does vision look like as a result of these considerations? Like, does that mean that, like, you're right, like, as models become more performant, as size becomes less of an issue, as we can start to do real time with higher quality, today that looks like the warring frameworks, if you will, of TensorRT and OpenVINO and whatnot from NVIDIA and Intel respectively. But you extend it over, like ignore those details, paper over those. Just imagine that we're 10 years, 20 years, 30 years in the future.
Mm-hmm.
What do you think like
Yeah.
the state of vision looks like?
Yeah, so I think I'll just start with kind of reflecting on the present day, just in the few years, that I've seen these sort of things evolving, and I think it's just incredible today that there's GPU resources available on, say, like Google Colab. For only $10 a month, you can be accessing a Tesla V100, and that's just given to you by default now, and that's insane, that kind of compute is out there and available, and I think naturally that's going to kind of only increase as time goes by. So the size of the models that are going to be able to deploy, the speed that they're going to be able to train, and their performance will just rapidly increase, say, in 20 to 30 years. So that means that the amount of data that is required to learn certain tasks and the size of the data set will be able to shrink, to be able to achieve these tasks. So you'll be able to bootstrap a lot quicker to new areas and new domains, which I think is exciting. And certain problems that we thought were unreachable before, like self-driving cars, for example, will be a reality. We'll be able to achieve those things. I don't know what you think.
Yeah, I mean, I think that's entirely accurate around the what. Like, I mean, the cost of training are continuing to fall. The amount of data that's collected and stored, doubles every couple of years. But the implications for that, I mean, given current circumstances surrounding the rise in inevitability of remote work, not just for office jobs, but for like remote sensing jobs, or like sending drones forward, or like, I mean, in 10 years we'll probably have our first broad scale augmented reality use cases. I mean, the vision isn't just like, if you think about it, like right now it's kind of like vision is a separate component part. It's like, okay, I gotta get my phone and start to do vision stuff, but like in a very short period of time it'll just be ingrained and an enhancing part of the way that we experience the world and the way that businesses and products, etc., can experience the world. And so the real-time understanding of the real world around us, as well as a computer can, with the context that a computer can provide, is just going to be, in a lot of ways, like trying to predict Uber when there first was, a backlink in the 90s, right? Like when you had ARPANET, who would have thought about Uber? Is like the same way that we're talking about vision now versus what's capable. And it makes for some really, really exciting capabilities that really excited to basically be a part of building that future.
Yeah, it's really an amazing time to be part of things.
Awesome. So I mean, from evaluating model trade-offs to the future of vision, really enjoyed this one. Thanks so much.
Yeah, thanks for being here, guys. Don't forget to like and subscribe below for more videos like this, and we'll see you on the next video.